This is Lecture 26. Today we're going to see how the discovery of electromagnetism profoundly affected the ability of natural philosophers to understand nature's forces and their interrelationships. We ran into this question in the last lecture. There we encountered the numerous ways nature's forces appeared to interact with each other at the end of the 18th and the beginning of the 19th centuries. We saw, for example, how static electricity could result in motive force. Electricity could move matter because it could be made to exert both an attractive and a repulsive force. And in the battery, we saw that electricity could be turned into chemical force when it was used to dissociate water into its gaseous components. Of course, electrical current in a wire got hot. Well, the wire got hot, so clearly it could be turned into the force of heat. And when the wire glowed, electrical force had become optical force. In the work of William Herschel and Johann Ritter, we saw how colored light could be linked to heat and chemical force. Well, that's not exactly right. The spectrum of colored light runs from red on the long end to violet on the short end. I'm speaking here of the respective wavelengths of the light. What Herschel and Ritter did was to show that on either end of the spectrum of visible light, there was a region that had properties different from those of light. Just below the red end, there was a region of heat. And just above the violet end, there was a region that had distinct chemical capacities. For want of a better term, we don't speak of radiation yet, we identified these regions by the colored light right next to them, infrared light and ultraviolet light. The significance was that light was being linked here to heat and chemical force. We noted at the end of the lecture that these and other connections among nature's forces led some to ask the general question about what lay behind the idea of force itself. Was there a single primal force of nature, of which all these other forces, motive, electrical, magnetic, chemical, thermal, optical, organic, all these were manifestations? It was a tempting prospect. And if it was true, then perhaps we could understand a great deal about nature if we could find out how the forces all could be unified into this one fundamental force. In fact, this question about the unity of forces was not confined to those who saw themselves as experimenters. It was also a central concern of the Romantic thinkers we encountered in Lecture 14. There we met Frederick whose nature philosophy inspired so many at the beginning of the new century. Recall that he rejected the notion that nature was a machine in favor of viewing it as an organism. Now, we don't have to go again into why he did that. Let's just focus on a key point we made when we examined his ideas. I mean that an important quality of organism in Schelling's thought was the way in which it unified disparate parts into a living whole. Organism unified everything under one roof, so to speak. It didn't leave anything out. Every aspect of reality, including the world of the mind in the case of humans, was part of the integrated whole experienced by organism. So since nature is an organism in Schelling's system, all of nature was an organized, interdependent unity, and it was held together by a world soul, just as the human organism is a coherent whole unified by a human soul. Well, naturally then, this meant that all of nature's forces were interrelated as well, since they were all parts of the larger organized whole. For Schelling's Naturphilosophie, or nature philosophy, it had to be the case that nature's forces were all interrelated. You should expect that one force possessed an intimate relationship with another. One particular relationship caught Schelling's attention. That was the relationship between electricity and magnetism. Where electricity and magnetism were concerned, Schelling taught specifically that, philosophically speaking, they were one and the same dynamic activity. Now, he had his philosophical reasons for saying that, and they needn't concern us here. Suffice it to say that Schelling's basic approach inspired those who were influenced by his thought to be ready to find interconnections among nature's forces, and that the relationship between electricity and magnetism held particular interest. One important figure from this period who was very much influenced by German philosophy was the Danish natural philosopher Hans Christian Ørsted. He went to the University of Copenhagen in 1793, just at the time when the works of Immanuel Kant were must-reading in Europe. Ørsted read a lot of Kant's work and was quite impressed. Kant, you'll recall, respected the need to begin with the data of the senses, to experiment, and to come up with mechanical explanations of natural phenomena. All that made sense to Ørsted. But he was a little uncomfortable with the sharp separation that Kant drew between the knowledge of the natural world and the realm of the spirit. They had nothing to do with one another in Kant. And young Ørsted had inherited from his Lutheran upbringing a strong sense of the spiritual that was very important to him. Somehow Kant's cutting out the world of nature from the realm of religion wasn't right for Ørsted. But still, Kant's achievement impressed him. By the end of the decade, actually in 1799, Ørsted completed his doctoral degree in philosophy. And soon after this, he made an extended trip to Germany and France. And I do mean extended, since he stayed there until January of 1804. It was well-timed because one of the scholars he met while he was in Germany was Schelling. Schelling was now all the rage. He was the young phenom that was attracting so much attention. The more Ørsted became familiar with Schelling's nature philosophy, the more he felt himself drawn to it, especially to one particular aspect of it. Ørsted liked Schelling's demand that all of nature must be regarded as an organized whole that was able to be grasped by our reason. He liked Schelling's insistence that Kant was wrong to separate our experience into two non-intersecting parts. And he very much agreed with Schelling's claim that to understand nature in its organized totality, you really needed to think of nature as a world soul. That notion melded very well with Ørsted's religious vision of a unity between spirit and nature. Of course, this notion of a unity between spirit and nature was very evident in Schelling's work. But for Ørsted, the unity meant something more explicit than it did for Schelling. For Ørsted, the unity of spirit and nature pointed to the presence of God, and that was extremely important to him. Ørsted spent a good deal of time in and around Jena, the center of the Romantic circle, and he also got to know some of the other Romantic natural philosophers. In particular, he met Johann Ritter, whom I mentioned a minute ago. In addition to his work on light, Ritter had taken up the question of the relationship between electricity and magnetism. So, Ørsted joined with Ritter as he conducted experiments. They didn't confine themselves merely to electricity and magnetism. They also asked how chemical force fit in. In fact, Ørsted became convinced that the best candidate for nature's one fundamental force, the one that all the others were forms of, was chemical force. He persisted in his experimental program, the one he'd begun with Ritter, right after he returned to Denmark, where he became a professor of chemistry in 1806 in Copenhagen. Now, it was much later, in the spring of 1820, when Ørsted gave a series of lectures on electricity, galvanism, and magnetism to advanced students at the University of Copenhagen. There's still some uncertainty about the sequence of events here, but one thing is very clear. The spring and summer of 1820 was a crucial time in the history of physics. You can find different versions of what happened. The one I'm going to relate is based on the most recent work on Ørsted, and I have every reason to trust it. As we've seen, Ørsted was convinced for philosophical reasons that electricity and magnetism were somehow related. So he was also confident that there should be a way to demonstrate that an electrical current could produce some effect on a magnetic needle. As he was preparing for his lectures, he thought about doing a test of the idea as part of the presentation. But then he thought better of it because he was having difficulty getting the effect that he sought. Then, in the lecture itself, he decided to try it again. I can imagine what likely happened. He explained to the students what he thought to be the case. Then he explained how he had tried to demonstrate the effect. Then, maybe on the spur of the moment, he said, well, let me try it again. And so he did, right there in front of the class. Well, once again, he couldn't get much of an effect. The demonstration didn't go well, and it didn't impress his listeners. This was in the spring. Later, that summer, he persisted in his attempts and was able to show that a magnetic needle was deflected when placed near a current-carrying wire. One of the reasons why all this was so difficult was that the effect he finally got was not at all the one he anticipated. Let me explain. What Ørsted discovered in the summer of 1820 was that if current flowed through a wire, then a circular magnetic force existed around the wire. He could show that by holding a magnetic compass in the vicinity of a current-carrying wire. Imagine a wire in front of you that carries current, and it's running from your right to your left. When Ørsted held the compass needle in front of the wire, the needle pointed up. When he held it on top of the wire, it pointed away from him. When he held the compass behind the wire, it pointed down. And when he held it under the wire, it pointed toward him. The force clearly acted in a circle around the wire. One way of summarizing things here is given by what's called the right-hand rule. If you curl your fingers so that they point in the direction of the magnetic circular force around the wire, then the current flows in the direction your thumb is pointing. Now, this was wholly unexpected because no one knew anything about forces that acted in circles. That wasn't like the action of Newton's forces or any of the other forces we've been talking about. They all acted in straight lines. So it's no wonder Ørsted had a tough time finding the relationship he was looking for. That was because he'd been looking for the wrong thing. Well, Ørsted announced his discovery, and it caused a great stir, as you can imagine. It also stimulated other experimenters to investigate this strange circular force. What was going on here? How to explain it? When Ørsted tried to explain it, he naturally resorted to the nature philosophy that had inspired him to look for the connection in the first place. He said that the production of a magnetic force by an electrical current was the result of what he called an electric conflict. To most of his contemporaries, this explanation was not something they could easily relate to. Most of them were not that much into Schelling to appreciate talk of nature's polarities and so forth. So Ørsted's appeal to nature philosophy to explain what he'd discovered was not persuasive to most people. Naturally, others also tried their hands at an explanation of this new electromagnetism. In fact, two very different approaches to understanding how electromagnetism was produced emerged very soon after Ørsted's announcement. In spite of their fundamental differences from each other, both had their merits, as we'll see. In fact, I think that the success of these two different approaches to the problem illustrates something important about natural science. And that's this: it's not always the case that there's but one approach. Sometimes nature is so profound in its structure that our best attempts to capture nature result in only one side of it. And there's nothing wrong with our depiction of that side. It can capture that side pretty well. But we ought not to get too cocky about it. We ought not to think that we've gotten the whole thing. Let me show you what I mean. One explanation of electromagnetism was given by the French mathematician and natural philosopher André-Marie Ampère. Prior to 1820, Ampère had established a modest reputation in French scientific circles through work in chemistry and mathematics. But we remember him for his work in electromagnetism. In fact, as you know, his very name, we say ampere in English, is used to this day as the base unit of electrical current. Well, Ampère assumed that any force, magnetic or otherwise, couldn't really act along a circular path, as Ørsted's description of the magnetic force around the current-carrying wire seemed to indicate. He believed that the circular path the magnetic force appeared to follow around the wire was the resultant sum of individual forces that acted in straight lines. He thought that the apparently circular magnetic force had to be the sum of what are known as central forces, that is, forces that act directly along a line between two centers of two masses, or two charges. Now, Ampère was a mathematician. He knew how to represent these central forces mathematically, and he knew how to add them up to get the circular result that was present around the wire. That was a complicated process, but he was up to the challenge. And he also continued to explore the relationship between electricity and magnetism experimentally. He decided to see what happened when the wire wasn't just straight, as it had been in Ørsted's experiment. He bent the wire carrying the electrical current, that is, he wound it around a bar of iron. What happened? Well, he found that he had created a magnet in the iron bar. He could summarize his results using the fingers of his hand. This time, however, he used his left hand, and he let his fingers curl in the circle followed by the electrical current. Last time they curled in the direction of the magnetic force. Well, in Ampere's arrangement, with the wire wound around the iron bar, if he wrapped the fingers of his left hand in the direction of the current flow, then his thumb pointed in the direction of a north magnetic pole. What did all this mean? Well, to repeat, for Ampere, there were only central forces, no circular forces for him. In addition, Ampere came to a startling conclusion. Magnetism, he said, was just electricity in motion. He reasoned like this. We know that static electrical charge exerts force. Two charged bodies either attract or repel each other, depending on the kind of charge they have. So if static electricity can exert force, why can't current electricity exert force? And the kind of force moving electricity exerts is magnetic force. Magnetism is electricity in motion. Now, this gave him the basis on which he could reason further about magnetism. At first glance, it might not seem all that promising. For example, take a permanent magnet. You know, one of those bar magnets or horseshoe magnets we've all played with at some time or other. What were the implications for understanding a permanent magnet if magnetism is to be thought of as electricity in motion? Where's the electricity that's moving when you have just a permanent bar magnet of iron? There's no electricity there. Ampere said that even in the case of a permanent bar magnet, there was electricity in motion. But where? He postulated that there was a circular flow of electricity around each molecule of the iron. So each molecule was made into a miniature magnet in the same way that he'd made the iron bar into a magnet when he wrapped the current-carrying wire around it. In each case, you have electricity moving in a circle around an iron core. In one case, the core was the bar of iron that was inside the wire wrapped around it. In the other, the core was the molecule of iron inside the circular flow of electricity around the molecule. And here's where his expertise in mathematics came in. Ampere wrote the complicated mathematical equations that described the forces that moving electricity exerted. He assumed the forces acted in straight lines perpendicular to the direction of the current's flow. And as a result, he was able to capture a great deal about the behavior of electromagnetism. He had a mathematical description of the forces involved. That's pretty much what Newton had done for celestial mechanics, to provide a mathematical description of the forces involved. In fact, Ampere's achievement marks the beginning of what's called electrodynamics, the forces produced by electricity in motion. This was an extremely important subject in the 19th century, especially in physics. To give you a hint at how important it would turn out to be, let me just indicate that Einstein's paper of 1905, in which he reasons to special relativity, is entitled On the Electrodynamics of Moving Bodies. That, of course, takes us beyond the 19th century, but I'll at least mention why electromagnetism was so central to the emergence of special relativity in the very last lecture of the course. Well, that was one understanding of electromagnetism that surfaced after Ørsted's discovery. I said there were two, and I said they were very different conceptions, so different that they each represent partial descriptions of a larger whole. What was the other? The other appeared in England and was the work of a natural philosopher named Michael Faraday. Now, Faraday's name has also made it into the vocabulary of electrical units, in his case twice. Once the Faraday for a unit of electricity in electrolysis, and again in the farad for a unit of capacitance. Faraday was a remarkable man for several reasons. And one is the background from which he came. He was born in 1791. His father, James, blacksmith, had become a member of one of the dissenting sects in England at the time. We've met dissenters before, Joseph Priestley, for example. But there were lots of different kinds of dissenters, and the one in which Faraday was raised was not the same as Priestley's. Faraday grew up among the small sect of religious dissenters known as Sandemanians. They had their origin back in the 1720s when a Presbyterian minister in Scotland named John Glass decided that the Bible hadn't said anything about associating the church with a nation, so he came to the conclusion that there was something wrong with the idea of a Church of Scotland. He persuaded some others, and they broke from the national church with the idea of forming a congregation that was going to be based solely on the Bible. The name Sandemanian came from Robert Sandeman, who had joined the group early and had in fact married one of Glass's daughters. It was Sandeman who was responsible for much of the growth of the group in the 1750s, especially outside Scotland. So in England, the group became known as the Sandemanians. Now, I'm telling you all this about the Sandemanians because historian Geoffrey Cantor in Britain, a biographer of Faraday, has shown how central it is to an understanding of Faraday. Faraday remained true all his life to the convictions he inherited from his Sandemanian upbringing. He believed in taking the Bible simply at its word, and that didn't present a problem for him, even as he rose through the ranks of British natural science and became famous in scientific circles. Faraday's unassuming manner, his devotion to a simple life, one whose ultimate meaning was expressed in his Sandemanian faith, was consistent with his simple and straightforward approach to the problems of natural science, in particular to electromagnetism. Let me tell you just a bit more about Faraday, and then we'll see how this works out. Because he came from a poor family, there was no possibility of much formal education for Michael. There were 4 children in the family. Michael was the third one. He must have shown signs of intelligence because he was the only one sent to a day school where he could learn how to read and write and do basic arithmetic. But that's as much schooling as he would receive. By age 14, he was apprenticed to a bookbinder. Everyone expected he would learn that trade and someday take on the profession. But fortunately for the world of natural science, it was not to be. Faraday was the kind of person who took advantage of his situation. For example, he read many of the books that came into the shop for binding. That, of course, imparted an education of its own sort. He was clearly the curious sort, and he got involved with a group of young men who were interested in natural science. They met regularly on Wednesday evenings. Faraday warmed to this subject. He began attending public lectures on natural science, like those that Humphrey Davy gave at the Royal Institution. Then an accident occurred that changed everything. Davy was temporarily blinded when he was doing a chemical experiment. By chance, someone recommended Faraday to Davy. He could serve as a writing assistant. That led a few months later to an opportunity to become Davy's assistant in the laboratory. This was just too good to pass up, even though it meant that Faraday would have to abandon plans to become a bookbinder. So he began to work under Davy's direction at the Royal Institution. As Davy's assistant, he learned quickly about experiments in electrochemistry and soon became something of an expert himself. In fact, Faraday would never leave the Royal Institution. He would be associated with it all his life, and he was destined to become even more famous than his mentor Davy. It's this unique background of Faraday that helps us understand the approach to electromagnetism that was so different from Ampere's. For example, Faraday didn't know mathematics, but he had a keen mind, and it's the combination of his mind, his unusual education, and his deep religious convictions that allowed him to come at nature in a way that was more open to new possibilities than that of most of his contemporaries. Where electromagnetism was concerned, Faraday didn't insist, as Ampere had, that nature's forces had to act along straight lines. He simply accepted the idea that some forces acted along curved lines rather than straight ones. So when he read what Ørsted reported about the behavior of the magnetic needle around the electrical current, he just visualized what he thought must be going on. He imagined in his mind curved lines of force, circular pattern in which magnetic forces surround a current-carrying wire. And then he built an apparatus that captured what he was visualizing. In the fall of 1821, he ran a wire that could carry a current straight down into a beaker filled with mercury. In the mercury, he rigged up a small magnet that floated on the surface, and then he turned on the current. What happened? The magnet rotated in circles around the wire as long as the current flowed. He could see at work the circular force Ørsted had discovered. He literally had traced out its path. And what he'd also done was to show that the continuous flow of electrical force could produce a continuous motion of matter. Perhaps he'd even converted electromagnetic force into mechanical force. About a decade after Ørsted's announcement, Faraday asked a new question. If a current-carrying wire produced constantly acting lines of magnetic force, then might not one be able to go in the other direction? Could you go from magnetic to electrical force? So he figured out a way to test the idea. First, he produced lines of magnetic force using a wire, something like the experiment I just described. Now he had magnetic force. Could he use that to create electrical current in a second wire? Could he induce electrical current into the second wire? All he got at first were little spurts of electrical current in the second wire. Once the magnetic lines of force were produced around the first wire and the current was flowing steadily, he saw nothing more in the second wire. So he focused on the spurts. When did they occur? They seemed to happen at the beginning of the process. The breakthrough came when Faraday realized that the spurts occurred when the magnetic lines of force were changing, which was happening when they were first being established. He soon realized that he could change the magnetic lines of force by interrupting them. And here's how he did that. He took a bar magnet and he allowed it to be wrapped with a wire that could carry current. So he had the standard arrangement for producing magnetic force using an electrical current. But he wanted to go the other way, to produce electrical current from magnetic force. Now the bar in this case was a bar magnet. So he had a magnetic force already. All he needed to do was to interrupt the magnetic force to see if that generated current in the wire wrapped around it. What he did was simply to physically move the bar magnet. And sure enough, as long as the magnet moved, current flowed. He now knew how to use magnetism to produce electricity. This was a new source of electrical current, and it would prove to be a profoundly important one. The reason was that discoveries like this one by Faraday, and you can be sure there were others who were uncovering different aspects of this possibility of inducing current from one wire into another, these discoveries made possible new inventions that had a huge impact on 19th century society. First, of course, was the electric generator. Faraday had generated electricity by moving the bar magnet inside the loop of wire. Why not then turn a loop of wire between two poles of a magnet? That would interrupt the magnetic lines of force, and in fact it proved an excellent way and an efficient way to produce electrical current in a wire. Next came the electric motor. Here you pass current through a coil of wire that's suspended between two stationary magnetic poles. Without going into it further, let me just say that what you can do in this arrangement is use the electrical current to produce a constant rotation of an armature. If you connect that armature to other machines, you can transmit the motion that you create to drive machines. You've transformed electromagnetic force into mechanical force. You can use electricity to do mechanical work. You can just imagine how wide-ranging the implications of that were. Faraday's visualization of what was going on, his idea of lines of force, gave rise to a new concept that would be enormously important to physical science in the 19th century. I'm talking about the notion of a field of force. The area in which the lines of force existed determined for Faraday a field of force. We'll encounter this concept again later. But in our next lecture, we're going to return to this question about converting force from one kind to another. We'll begin with the ubiquitous force of heat. And, as in today's story, we'll encounter more challenges to Newtonian ideas that will open up new vistas for physics.